72 kilobytes of memory, 2 megahertz of processing power. And this source code, written by hand, in assembly language, landed humans on the moon. Today, I'm opening the original Apollo 11 guidance computer code, the same code that flew Neil Armstrong and Buzz Aldrin to the lunar surface in 1969. And I'm going to walk you through what these brilliant engineers built with less computing power than your bathroom scale. But first, some context. Programming has gone through a dramatic evolution. In the 1950s, you fed punch cards into room-sized machines. By the 60s, assembly language let you write mnemonics instead of raw binary. The 70s brought C. The 90s brought object-oriented programming. The 2000s gave us the web. And now, in 2026, AI agents are writing and debugging code autonomously. This timeline matters because the Apollo code sits right at the beginning, at the assembly language era. And what they accomplished there, with those constraints, is staggering. Let me put this in perspective. The Apollo guidance computer ran at 2 megahertz. Your phone runs at 3400 megahertz, 1600 times faster. The AGC had 72 kilobytes of ROM. Your phone has 512 gigabytes, 7 million times more. The AGC had 4 kilobytes of RAM. Your phone has 12 gigabytes, 3 million times more. And yet, that tiny computer got 3 men to the moon and back, safely. This is the Apollo guidance computer, built at MIT's Instrumentation Laboratory. Each memory module, the core rope memory, was literally hand-woven by workers at Raytheon. Copper wires threaded through and around tiny magnetic cores. A wire through a core meant a 1. A wire around a core meant a 0. They called it LOL memory, little old lady memory, because the weavers were so skilled. Once woven, the code was permanent. You could not update it. There were no patches in space. And here's what still gets me. Assembly language is still the foundation of everything we do today. Every Python script, every React app, every AI model inference, it all compiles down to machine instructions. Understanding the low level makes you a better engineer at every level above it. The AGC engineers had no compiler, no debugger, and definitely no Stack Overflow. They wrote every instruction by hand. And it worked. This code base is a masterclass in foundation. Low-level knowledge is a cheat code. When you understand how the machine actually thinks, at the level of logic gates, registers, and memory addressing, every high-level abstraction you use today makes so much more sense. And those exact constraints are still relevant right now in the AI era. We are hitting memory walls again. Fitting a 70 billion parameter model into 80 gigabytes of RAM requires the exact same optimization mindset. We use quantization to trade precision for memory. We unified RAM between the CPU and GPU. The hardware has changed, but the physics of computing remain exactly the same. So when I found this repository, the original Apollo 11 source code, digitized from paper printouts at the MIT Museum, I felt a genuine spark of interest. This was pure assembly language, the same low-level primitives we use to build operating systems today, but used by some of the most talented engineers who ever lived to do something no one had ever done before. I had to open it up and see what they built. And here's what struck me. The modern fundamentals we still teach today. Logic gates, registers, memory management, basic algorithms. Those are the exact same primitives these engineers used. But they took those fundamentals and built a real-time operating system from scratch. Lunar navigation with fixed-point math, a crash recovery system for deep space, and code that actually landed on the moon. Same building blocks, wildly different ambition. All right, let's open the code. This is the Apollo 11 repository on GitHub, originally digitized by Ron Berkey with scan images from Paul Fjeld. It is public domain. Anyone can read it. The code is split into two computers. Comanche 055 ran on the command module, the spacecraft that orbited the moon with Michael Collins. It handles navigation, re-entry, and rendezvous. 85 assembly files, 1,751 pages. And Luminary 099 ran on the lunar module. This was the computer that actually landed on the lunar surface with Armstrong and Aldrin. 91 files, 1,743 pages. This is where the lunarlanding.agc lives. The build system is interesting. There is a file called main.agc that includes every source file using $ directives. You see, in the 1960s, they had no linker. The entire program was assembled as one monolithic blob. It was like inserting your deck of punch cards into someone else's deck. 100 files assembled together, and every single include has a comment showing the page number from the original NASA printout. So you can cross-reference it with the scanned images at the MIT Museum. Now this is my favorite file in the entire repository. Burn, baby, burn. Master ignition routine, .A, G, C. The name comes from Magnificent Montague, a disc jockey in Los Angeles in the 1960s who used to shout, "Burn, baby, burn," when spinning the hottest records. Don Iles, one of the engineers who wrote this routine, explained the origin at the 40th anniversary celebration of the moon landing. The master ignition routine is the universal engine startup sequence. Every powered flight program on the lunar module, P-12, P-40, P-42, P-61, P-63, all of them call burn baby. It is table-driven. Each program loads its own constants and callback addresses into a register called which, and the ignition routine indexes into those tables. Elegant, reusable, and remarkably modern in its design pattern. The comments even include Latin inscriptions. Honi soit qui mali pens, shame on him who thinks evil of it, and noli se tangere, touch me not. These engineers had personality. The lunar landing.agc, program 63, the braking phase. This is the code that was running when Armstrong looked out the window, saw a boulder field, and took semi-manual control. The algorithm uses iterative convergence. The DDUM calc routine adjusts the ignition timing until it converges within a threshold. And one of my favorite comments reads, "Astronaut, please crank the silly thing around," referring to the landing radar antenna that needed to be repositioned manually. And then there is Flagorgy. Yes, that is a real label in the code that landed humans on the moon. The comment says, Dionysian flag waving. It is the initialization section of the lunar landing program, clearing and setting the flags that control every life or death decision during descent. MUN flag, NA throttle, red flag, LRBY pass. Each one of these flags determined whether the engine fired, whether the radar was active, whether an abort was possible, and someone named it Flagorgy. What blows my mind is that they built a real-time operating system from scratch. The executive is a priority-based job scheduler. It runs the most important task first. The waitlist is a timer-driven task queue. The cron job of 1969. The interpreter is essentially a virtual machine that runs a higher-level language for complex math, vectors, matrices, trigonometry, and the restart system. If the computer crashed mid-task, it could recover and pick up exactly where it left off, in deep space, in 1969. Pinball game buttons and lights. This is the code for the DSKY, the display and keyboard unit. It is one of the largest files in the code base. The astronauts communicated with the computer using a verb-noun system. You typed a 2-digit verb code, then a 2-digit noun code. Verb 06, noun 43, display latitude and longitude. Verb 16, noun 85, display the countdown to ignition. Imagine flying a spacecraft with a calculator keypad and a set of 7-segment displays. And then, the 12:02 alarm, the most famous software moment in history. During the landing, the computer started throwing 12:02 and 12:01 alarms. Executive overflow, too many tasks queued for the processor to handle. But here's the thing. This was not a bug. It was a feature. The AGC's priority scheduler shed low-priority tasks to keep guidance running. The navigation and landing equations kept computing, while less critical tasks were dropped. Steve Bales, the guidance officer in Mission Control, made the call. "We are go on that alarm." The software saved the mission by gracefully degrading instead of crashing. Now let's talk about what makes this code truly remarkable from an engineering perspective. The memory constraints. 72 kilobytes of ROM, hand-woven core, rope memory that took weeks to manufacture. Once it was woven, that was it. No updates, no patches, no over-the-air fixes from Mission Control. 4 kilobytes of RAM, magnetic core memory with destructive reads. Every time you read a value, it was erased and had to be immediately rewritten. No floating point hardware. All the navigation math, trigonometry, orbital mechanics, gravity compensation, done in fixed point arithmetic. And bank switching. Only 2 kilobytes of code were visible to the processor at any time. The rest was paged in and out as needed. Think about the math for a moment. Orbital mechanics requires trigonometry. Trig requires floating point precision. But the AGC had no floating point hardware. So the engineers chose scaling factors for each variable to maximize precision within 15-bit words. Double precision used 2 words, 28 bits of Mantisa, manually managed. They had to track the decimal point in their heads for every variable across the entire code base. Modern GPUs have more floating point units than the AGC had total transistors. And here is the punchline. In 72 kilobytes, they fit a real-time operating system with priority scheduling, lunar landing guidance equations, stellar navigation, and orbital integration, an autopilot for RCS jets, and engine gimbal control, a complete display and keyboard interface, and a crash recovery system. 72 kilobytes. Today, that is one website favicon, half a React component, a single high-resolution emoji, about 4 tweets worth of text. Let that sink in. Margaret Hamilton and her team at MIT wrote every single line of this code by hand. No IDE, no autocomplete, no syntax highlighting, no AI pair programmer. Just printed listings, pencils, and brilliant minds. She coined the term software engineering because she believed software deserved the same rigor as hardware engineering. She was right. In 1969, engineers wove code into copper wires by hand. Today, AI agents write, test, and deploy code autonomously. The gap is 57 years. But the fundamentals have not changed. Registers, memory, instructions, control flow. It is all still there, underneath every abstraction layer we have built since. Understanding the low level will always make you better at the high level. The best code is not always the newest code. Sometimes it is the code that got humans home.